what are the topics, guys, like your rectifier circuit and your amplifier circuit. In all the cases what we have seen that regarding your amplification, right? So now the topic we are going to observe in half wave, full wave, both the cases we have seen that your output should be rectified. Okay, that rectified output is not pure DC, so that what we are using some other circuitry, like your transformer circuits are used for your AC signals, and that will generate your smoothing DC output, but it is not up to that level at the rectifier output. So we need some filter circuit at filter level also. If you see, filter in the sense of the combination of resistor and capacitor. Okay, so that is also not that much of smooth signal. So what we need to get a pure DC signal. So if you see it here, a pure form of smooth DC signal, if we use the regulator, voltage regulator, the output of that is a pure DC form. That's why we should go for the voltage regulator circuit, guys. And typically the voltage regulators are available in the form of IC. Nowadays it is available very lightweight size and convenient to use. Earlier it was so bulky to design, but now because of the semiconductor industry revolution, it they developed the IC packages of voltage regulator, right? So in this voltage regulator, guys, directly I'll come to your slide. What is the purpose of getting the voltage regulator? Irrespective of the fluctuation in your input side, okay, uh, so what I will say, if there is a variation in the input side, irrespective of that, you should get a constant output voltage, constant or stable output voltage. Okay, so we are calling that as regulated DC. So how do we get that? Okay, so that is our focus. Directly, just a moment, I'll come to that particular slide. So okay, guys, there are different type of regulator actually. Series regulator, shunt regulator, and line regulator, load regulator. Different type of regulator circuits are there, but we are preferring to use the series type of regulator along with your load regulation. Okay, so for that sake, just have a look at the circuit. The notes are already uploaded in your Vita, so just have a look. Why? Huh. So if you see the circuit, what are the main parts of the circuit? If you focus on the circuit, we have the reference voltage part, we have the error amplifier part, which is called as error detector circuit, the altogether error amplifier, then one feedback path, feedback circuit, then one transistor. So these are the part of your voltage regulator. So now we are going to analyze the circuit. So basically, if you see, this is nothing but, this part is nothing but your op amp, and this is your transistor. Okay, so here we are using the emitter follower circuit. This part along with the op amp, if you see, we are calling this the arrangement emitter follower. What is the purpose of emitter follower? For impedance matching. Okay, it uses the principle of common collector, and for high to low impedance, it will give the stability. It means altogether we may say the circuit will provide the stability towards the impedance matching. So one by one we are going to study the property of the element used to make the voltage regulator. Now we will first focus upon in the circuit what are the other known parts in the circuit, guys. Can you see and tell me what are the other known parts? What do you say this part? What is the significance of this sign? Which diode? Zener diode, right? Okay, Zener diode. So what is the property of the Zener diode? Yes, Anyone can answer the property of the Zener diode. Guys, for the voltage regulator, actually what we are doing, we are combining the property of the Zener diode, and here we have the resistor. All together will gives rise to the nature of voltage regulation. Okay, Zener diode with the series pass transistor. So these are used for voltage regulation. How does it make? So first, if you observe, the Zener diode can be behave like as a normal diode, as well as it normal diode means it will rectify, or it will pass the current through it in the forward bias as well as in the reverse bias. Okay, so forward bias, it passes the signal smoothly and it will behave like a normal diode, but in the reverse bias also it is capable of passing the current through it. How means, when the breakdown voltage will reach, and at that time it will allow the current to pass through it. That is the property of the Zener diode. It withstands at the reverse bias voltage also, or reverse supply voltage also. It allow the current to pass through that, and that's why it need for stable uh, or for stabilization, it need one more resistor to protect the circuit. That's why we need this V reference signal to become or to build the V reference voltage. We need to take the help of the Zener diode and one series resistor for the voltage regulation. Okay, this is up to this part, and that is connected. You can see that this part is connected to the positive terminal of the op amp, or we can say the non-inverting input terminal of the op amp, but it is connected to ground. So this part is stable part, a fixed part. We no need to do with that. Just we have to check, irrespective of the fluctuation in the voltage, it will gives a stable voltage to the positive input terminal of the op amp. Now just have a look to the transistor part. If you see the transistor part, the base of the transistor, emitter, base and collector. This base of the transistor is connected at the V0 dash. Suppose this is the V0 dash and this is suppose V0. Now whatever the output through the emitter, it is connected to the output V0. The transistor is the intermediate part in between the V in and V out, so that we can say that the transistor is placed in series with your V in and V out. Now whatever the change in the V out voltage V0, we may get a change at this potential also. Suppose this potential is beta. What should be the beta value at here, and how much voltage will appear here? If you calculate the beta value, what should be the beta? Who can say? R3 whole divided by R2 plus R3, right? And what should be the voltage at here? It is beta V0. The voltage appear at this junction will become beta V0. Yes or no? The voltage at this point, and the all together is called as a sample circuit. Okay, the combination of this potential divider part is called as a sample circuit, and the voltage of sample circuit is nothing but beta V0 by the voltage divider concept only. So now just have a look. Here the input is connected, the beta V0 is connected another input of the operational amplifier, which is your inverting input voltage or the negative input voltage. Input is now connected to negative input of op amp. So if it is following the inverting configuration of op amp, obviously the output will be phase shifted. Yes or no? Here you are getting positive voltage and here you are getting negative voltage. So obviously if you consider the current input is now negative, the output is also negative at here, and here already a positive voltage is there. It will compare the two value. If there is a mismatch in between this and this, there will be some error. There will be some error, and that's why it is called as error detector circuit. The entire circuit is called as, up to this part, along with the sample circuit, it is called as error detector circuit, and which is labeled as V0 dash. Suppose this V0 dash is now applied to the transistor base Q1, okay, or the uh, series pass transistor Q1. Now, if there is a fluctuation in the input and we have placed a reference voltage at here, irrespective of all the changes in the input, the transistor will balance by taking this V0 dash. Whatever be the change in this V0 dash, it will always give rise to this V0, because we are using the Zener voltage as the reference voltage, because it will withstand in the reverse bias voltage also. It will balance the circuit. Even though there is any error, it will just balance the circuit. And here suppose any fluctuation is there in this negative terminal, this Zener voltage will manage that, and it will make that there should not be any difference in between V0 dash and V0, and it will give rise to a stable voltage at here. And so that irrespective of change in the input, we may get a constant output voltage. That is the property of your voltage regulator. Okay, and we can say that we will get a controlling output voltage because of this different type of circuit arrangement. So this is the internal part or operation of the voltage regulator. But nowadays switch type of regulators are also available. This is internal circuitry of voltage regulator. But if you go um, in the recent development of the voltage regulator, you may see this type of voltage regulator, which is called as IC regulator. Now it is available in the form of IC. Now guys, I'll just show you the internal circuit part. That Zener diode, that series pass transistor, your resistor, error detector amplifier, all are clubbed into this IC part. And here additionally you can use the load. Okay, so all together again it will frame a voltage regulator IC. So now you can see that in means input, out means output. The entire transistor can be labeled at here in this part, and it is grounded at the middle part. Base of the transistor is now grounded, and the Zener diode is also connected internally to the circuit. Okay, so that what we may get at the load resistor RL level, we may get the load regulation as well as line regulation. You just go through the formula of load regulation and line regulation. What is the meaning of that? Already it is there in your slides. Okay, so load regulation formula means, if you go for your no load condition, the difference in between no load to the full load, and if you take the ratio in between that no load, the difference in between no load, full load, and the ratio in between that and the full load is called as the load regulation. Okay, so how do we achieve that? You can easily calculate it from the formula. And line regulation means just change in the output and input. If you calculate the ratio in between them, then proportion will become in the form of line regulation. So what are the things you have to focus in this voltage regulation means, how do you get the regulated output means, through an example we can see. Circuit will look like this guys, and the numbers are LM317. This is also one voltage regulator. And guys, here one thing I will say, the formulas are there. For V0 formulas are there. And here some rated voltage are there that will be given to you for the calculation. Like suppose this is LM317, and here we are not showing you the internal circuitry, but we are going to calculate the V0 from here. So what are the V0 or what are the voltage contributing to calculate your V0? So here same beta network, this is your beta network value, R1 and R2 corresponds to give the beta network. And here guys, if you see, this R2 is not a fixed type, it is a potentiometer type. Okay, a potentiometer we have to use. So the V pot voltage across this and this, which is beta V0 only, potentiometer voltage, And another one across R1 we are getting reference voltage VR, and across R2 we are getting the potentiometer voltage. This reference voltage now guys, if you remember your Zener diode voltage and series pass transistor altogether will be similar. So that reference voltage and potentiometer voltage. Now if you see what is the potentiometer voltage in this case, let's have a look. What are the factors coming for that? Your transistor current IQ is approaching towards that. Okay, then IR, here the reference current IR1, so that's why IQ plus IR1 whole together multiplied with your R2 will gives rise to your V pot voltage. V equal to, because IR. So V potentiometer voltage is nothing but IR1 plus IQ. So if you solve it further, your V naught is nothing but 1 plus R2 by R1 into VR plus R2 IQ. So here in the equation itself, suppose this question has been asked to you, design an adjustable positive voltage regulator with the type of LM317 for an output voltage V0 to vary from 4 volt to 12 volt and output current I0 will be 1 ampere. So design the circuit. For that sake guys, see what is the formula just now we have studied. V0 equal to V reference whole into 1 plus R2 by R1 plus this IQ is nothing but your adjustable current. So some data sheet value will be provided to you guys. If not so, you just remember maximum adjustable current for LM317 is 100 microampere. Okay, and typical assumptions for R1, let's take 240 ohm, and here V reference is 1.25 volt for LM317. V reference is fixed 1.25 volt. And this value R1 value may be given to you in the question itself. So after getting the data, you can apply all the value. V reference is known now, so R1 is known, adjustable current is also known. What are the unknown value at here? If you solve this equation, we may get R2 equal to 0.52 kilo ohm. This data you have to calculate. R2 and R2 you have to solve to calculate the value. So V0 for 4 volt you have to solve once. This is case 1. And V0 for 12 volt, case 2. In both the cases you have to solve by using the same formula. That's all. In both the cases what you got? In first case R2 you got 0.52 kilo ohm, and in second case you got 2.01 kilo ohm. It means when the given value of your V0 is changing, this R2 value is also changing. If you increase more, this value will also increase as per the given V0 value. Like this type of question only we are asking, but with little bit twist that you have to remember. Okay. Suppose guys, in this case of circuit construction in the earlier circuit, I have given the example of the BJT type of transistor. If FET will be given, what are the changes it will happen to the circuit? That also you have to focus. If in spite of transistor, if the FETs are there or MOSFETs are there, what will happen to the voltage regulation? Because you know the property of the NPN and PNP transistor or BJT and FET and MOSFET, you just apply that concept at that time. Okay, so that's all for voltage regulator. You just focus upon 2.5 module, except your log and anti-log amplifier concept. All 3 modules are coming in your CAT 1 exam. Okay, do you have any doubt? Guys?
No, ma'am.
Okay, no doubt. So